Now we are going to consider the case in which we have a second order system and then we add a pole to it. So before moving forward, keep in mind that if we have a first order system, let's say we have a system with a pole here, if we add a second pole to this system, if I add a second pole to this system, the system simply becomes a second order system which we already have considered. So we will not go through that, okay? But instead we are going to take into account a second order system where we have two complex poles, and then we will see what happens when we add an additional pole to this system. So this is indeed what we are going to do. We have originally a second order system with two complex poles over here, and then we want to see what happens to the response of the system if we add a pole, let's say, somewhere, yeah? And since we are going to add a single pole, it will be a real pole, obviously. Okay, so we can, as we will see later, different cases, the single pole that we add might be closer to the origin, or it might be further from the origin with respect to the two complex poles that we have for our system. And then we will see if the single pole which is added is far enough from the origin, then we can neglect its effect. But as the single pole moves closer to the origin, its effect on the step response of the system will become more and more. So it will change the response of the system more strongly when it moves towards the origin. It goes closer to the two complex poles that we have. However, when the pole is further from the origin, we will call the two complex poles that we have as the dominant poles, as they will determine the step response of the system, yeah, with some effect from the additional pole. If we assume that the two complex poles that we have are located at minus zeta omega n plus minus j omega n times the square root of 1 minus zeta squared, and then the additional pole that we add is located at alpha r so over here minus alpha r and minus zeta omega n for the real part of the complex poles, then we can write down the response of the system, the step response of the system in the S domain in this form. We will have three terms for it, A over S plus the second term plus the third term, which comes directly from the effect of the additional pole. So D over S plus alpha R. And then in the time domain, we will have three main terms as well. A times U of t plus the decaying exponential times some sine plus cosine terms plus d times e to the power of minus alpha r times t. Okay, so this comes from the additional pole that we have. Then we can have three cases in it. The first case, as we refer to it as when the alpha r is equal to alpha r1, is the case when the real part of the additional pole is not much larger than zeta omega n. So it is somehow close to the complex poles. The second case is when the real part of the additional pole is much larger than zeta omega n. So it's indeed this second case over here. The first case is here. And the third case is when alpha r is at infinity, meaning that we don't have the, in some sense it means that we don't have the additional pole, okay? And that's when we have the second order system with two complex poles. So we have case 1, case 2, and case 3. Over here in the graph you can see different parts of the step response drawn for those three cases. If I start by case 3, we know that for case 3 we will have only a u of t plus the second term, e2 minus zeta omega nt times the cosine and sine. And basically for this case, d will be equal to 0. Okay, so the only part of the response will be this curve that you see here. So this is for case 3, and it is the complete response. Then if I consider the second case, case 2, for case 2, which is this case over here, and for that case we know that the additional pole at minus alpha r2 is let's say far away from the complex pose that we introduced. We will have two main parts for the step response. For this system, one main part will be a plus a ut plus e to the power of minus theta omega and t times the rest. And the next part will be d times e2 minus alpha r2 times t. And you can see over here that the first part of the response will be drawn here. And the second part of the response, d times e2 minus alpha r2t, is drawn here. And you can see that this part, let me highlight it, it decays quite fast, because after a short time you see that it is equal to 0. Okay, and that's because of alpha r2. As alpha r2 is large enough, then the e2 minus alpha rt times d will decay quite quickly. It will become 0. And as a result, the transient response of the whole system will be affected by little amount, let's say, at the beginning. While for the third case, as you can see here, when the additional pole moves closer to the two complex poles that we had, the part of the response which comes from the additional pole grows in terms of the amplitude, and also it decays slowly. So you can see that it is kind of decaying at the moment when the response from the other part of the response, let's say, decays at the same time. So it will have a longer effect, yeah, let's say. And you can see here the first part of the response, and it is kind of quite different than what we had for the case with no, let's say, additional pole. Obviously, if you add these two to each other right at the beginning at 0 plus, the response will be equal to 0, but then the shape of the response will be different than the case that we had for this. So having this in mind, we can say that for case 2, when the additional pole is far away from the two complex poles that we had, we can approximate the system, approximate it as a second order system. If the additional pole is far enough from the main ones, let's say. But for the first case that we had here, for the case 1, we cannot have such an approximation. We will see that this additional pole has some effect. Which kind of effect it has? It will have some kind of delaying effect, as we'll see in the next slide. Yeah, let's go through this slide. So in case 2 that we just discussed, the pure exponential dies out much more rapidly than the second order underdamped response. We just had seen it. It dies out at this moment, while the oscillations that we have for the second order system dies at this moment, let's say. Okay, so we can also say that if the pure exponential that we have, the pure exponential part for the step response, decays to an insignificant value at Tp, so at time Tp, if we have a very small value for that pure exponential part of the response, then we can say that the response is close enough to a response of a second order system, which is the third case 3. Yeah? So Tp for the second order system is here, and you can see that at Tp the contribution that comes from the purely exponential term here is almost equal to 0. So we can say that this case 2 could be approximated by case 3. However, in case 1, the post-transient response doesn't decay fast enough. So the second order approximation will not be valid. And then if we plot the whole response of the system, we will see how different it is from the response of a second order system. But as a general rule, we will use this second order approximation when we have alpha r bigger than 5 times zeta omega n. So if it's bigger than this, if alpha r is bigger than 5 times the zeta omega n, we say that the second order approximation is valid. If it's not bigger, then it is not valid, and we will see how to deal with that. In this example, which is shown here, we can determine whether the second order approximation for the systems is valid or not. You can see the value for alpha r as 15 and 4 over here. We have the value for zeta omega n. So for G1, we have 2 zeta omega n equal to 4. Zeta omega n is equal to 2, and alpha r is equal to 15. So we can see that alpha r is bigger than 5 times zeta omega n, as 15 is bigger than 5 times 2, which is 10. So for the first system, the second order approximation will be valid. You just need to keep in mind that the DC gain of the approximated system and the original system should be the same when you approximate it. For the second case, for G2, we have 2 zeta omega n equal to 2, so zeta omega n is equal to 1, and alpha r is equal to 4. And we can see that alpha r is not bigger than 5 times zeta omega n, so this is not valid. Okay, so as a result, the second order approximation will not be valid over here. Something to keep in mind is that as the value of alpha r increases, as the pole moves away from the origin, as the additional pole moves away from the origin, the value that we have for d decreases as well. So you can see it over here. Yeah, d is here. As alpha r gets bigger and bigger, this d becomes smaller and smaller, and as a result, the contribution that we have from the additional pole gets smaller and smaller, so its effect becomes less. In general, the additional pole that we have for the systems will have some sort of delaying effect, and it will be clear if you have a look at this solved example over here. So we have 3 systems. The first system, G1, is a second order system, and under them second order system. The second system, G2, is an under them second order system with an additional pole at -10. Okay? And you can see that for this case, 2 zeta omega n is equal to 4, so zeta omega n is equal to 2. For G2, it is also the same, but we have alpha r equal to 10. So it is indeed alpha r is in this case equal to 5 times zeta omega n. Let's say at the border. And then we have the third system, G3, for which we have the same zeta omega n for the, let's say, 2 complex poles that we have, but alpha r in this case is equal to 3. So for G3, we have alpha r equal to 3, and we can see that alpha r is not bigger than 5 times zeta omega n. Okay, so this is not valid. So we cannot use the second order approximation. Or let's say the response that we get for G3 will not be very close to the response that we get for G1, while what we get for G2 will be pretty close to G1 indeed. Yeah. Over here you can see what we get for the time domain expressions. As for the C1, C2, and C3, the step response of the systems in the time domain. And over here you can see how they look like. Okay, C1 is what we get for the second order system. So this is what we get for the second order system with no additional pole. Then C2 is when we have the same system with an additional pole at -10. You can see the time domain expression over here, and then the response is also drawn here. If you compare it with C1, it's kind of a delayed version of C1, and it is also taken down a little bit. Okay, that's because of this negative coefficient over here as well. So C2 is a delayed version of C1, but the amount of the delay is not big because the additional pole that we have is kind of far from the origin compared to the two complex poles that we had. And finally, in the case of C3, we can see that you can find out the expression over here. First thing to notice is that the term that we had for the coefficient that we had for the delay term, D, isn't that small compared to C2. It is 1.14, while for C2 it was 0.29. And then if you look at the graph, you will see that the amount of the delay is bigger, and the response has taken down more if you compare it with C2. So we can see that as the additional pole moves closer and closer to the origin, the effect of the additional poles becomes more and more. It changes the step response of the system more as it moves towards the origin and it gets closer to the complex poles. So these are what we have considered. You can also take into account the case when the additional pole that we have for the system goes closer to the origin compared to the complex poles that we had. If you take an example into, let's say, account, and then check out the step response of the system with and without the additional pole that we have, you will get an understanding. As the additional pole moves towards the origin, its effect will become more and more, and let's say it will become more dominant. Yeah, if it goes closer to the origin compared to the complex poles, you will see that its effect will be bigger than the effect of the two complex poles that we have for such a system. Okay, so that's all for this video lecture. In the next video lecture, we will consider the effect of the zeros, and you will see what happens to the response of the system when our system has one or more zeros. Thank you for watching this video.